Now we consider another important example. Suppose there is an oriented surface. Oriented surface means that a surface usually have two unit normal vector. Taking one unit normal vector gives an orientation of the surface. So such a surface is called oriented. Of course, there are some surface which is not orientable, such as the Mobius band and also the Klein bottle. We will not study that surface here. We only study those orientable. Then the orientation is given by a normal vector. Okay. All surfaces we studied are orientable. So maybe I will say something about oriented surface. S is a surface then is a normal vector on S, which is not zero. But we normalize this vector. Because it is not zero, the norm is always not zero, so we can divide it by the norm. So this is a unit normal vector on S. Actually, this is a vector field. Vector field is nothing. It's not very difficult. Every point on the surface you indicate a vector, so you obtain a vector field. Therefore, vector field is simply vector valued functions. Nothing strange. Okay, so this argument means that every surface we considered are orientable, and an orientation can be given by this normal vector. Of course, you can also consider the reverse direction normal. Then this is another orientation. Okay, so surface has two orientation. Now, suppose we have a floor. We have a floor. We have some floor. For example, a river, and we have a surface as here, and the floor velocity of a floor is v, a vector field. At every point on the floor, you have a velocity. Okay, so maybe I will add a floor here. Okay, and so at the point on S, we want to consider how the volume of a floor passing through this surface in unit time. The question is, we want to find volume of a floor passing S per second. Okay, so how to solve this problem? We take a point X. The idea to solve this problem is that take a point X in S. So suppose this is the point. Suppose this is the point on S, denoted by X. Then we take a surface element d sigma about this point. That is a small piece of surface a small piece of surface containing this point. This is d sigma. Then assume that the unit normal vector consistent with the orientation at the point x is n. This is n. Then we declare that the volume of flow, passing d sigma per minute per second is dv equal the inner product of v. So this is v, the velocity, and the n multiplying d sigma, the measure of the surface element or the area of the surface. Okay, so this is the crucial point. It is not the norm of v multiplying the area, because if your flow tangent to the surface, then your velocity is a tangent vector of the surface. Such velocity along this flow line, the liquid will not passing through the surface. So such velocity has no contribution to the volume we computed. Only those normal component of the velocity counts. Okay, therefore this is why we need to compute the inner product of v and the normal vector n. This is precisely the normal component of the velocity. So this is the volume of flow passing through these small pieces of the surface. Now we want to compute the volume through the whole surface in unit time, maybe per second. How to get this integration? Thus, the total volume passing through S in unit time is the integral over the whole surface of this volume element, that is this surface integral. So you take the inner product of the velocity, which is the normal vector, which is the unit normal vector. Equivalently, you take the normal component of the velocity. This is a real valued function. V is vector valued, but its normal component is real valued. So this real valued function integrating over the surface give you the total volume of flow passing the surface in unit time. Okay, so this example tells us that we need to study surface integral of the form but we traditionally such kind of integral will also be denoted by this. That is the area in the first notation in this integral. The area is a real number. is a non-negative number. The measure of the small piece of surface, the area element or surface element. Okay, it is not a vector, but we did not define the oriented area element, oriented surface element by the normal, by consider this as a vector which the same direction of the normal and which the norm, the measure of the surface element. So this is the oriented surface element. Using elemented surface element, our integral can be written in this way. So in the study of flow and something similar problem, we always need to compute integral in this form. But this integral is nothing new. It is simply a convenient way to write the above integral, the usual surface integral. Okay, but anyway, we need to, since this kind of integral appears frequently, we need to study this more generally. Okay, so this is the definition. Suppose S is an oriented surface. The orientation is given by a unit normal vector field. Oh no. And capital F is a vector valued function defined over the surface. Continuous. Then we defined the flux integral of F over S is in notation, but this is precisely so. In other words, flux integral is simply the usual integral. Flux integral is a convenient way to write this special class of the usual surface integral.